or down, I don't know. And okay, we'll tell you when you have 15 minutes.
Okay. All right. Well, I'm really delighted to be here. Thank you to the organizers first for organizing such a gathering of.
Paul is coming from Oxford.
Yeah. It's okay. Yeah, it's such a gathering of combination of people at all stages in their career. It's a lot of fun, and of course you for coming. So yeah, Eduardo said in his introduction this morning that the purpose of this was to bridge the two communities. So there's my attempt to draw that. But what he didn't say is what we were bridging. And so this is my version of, okay, so we've got a canyon here. This is the Grand Canyon between the two fields. And this is where I live. Because and what I do, at least most of the time in my life, is lattice statistical mechanics, which doesn't really belong to either field. So for political reasons, one typically has to, if you're a physicist, one has to pretend you're one or the other. But we really live down here, and as long as we're on the subject here, then the mathematicians are up here somewhere and with an airplane. And we kind of occasionally all signal up to them, and then they beam something down. But actually, there's some mathematicians down here, too, and maybe I'll say a little bit more of that as I talk. So we who do this get to talk to some interesting mathematicians that everybody up here doesn't always pay attention to. So anyway, sometimes. Anyway, in fact, when I gave my title to the organizers, I put lattice in there, especially to distinguish my talks from John, who will be talking about at least things with a bit of overlap. And I'll mostly focus on the lattice. And sometimes people apologize for that, so I'm going to do the opposite. I'm going to tell you why I think it's certainly as good and often a better idea to do things on the lattice. So these are reasons why lattice. So blue shows up okay up there. The red is bad. Okay. So anyway, some reasons. Well, one, and let's not underrate the value of simplicity. So we'll get to this bit in a minute. Over there, but writing down things concretely is a good thing. I know in the HEP side this doesn't happen, but it exists in the world. Materials typically, or often, solid state materials by their name, they're on the lattice, so it's there. And it's true, not always, but many times, where the concept, the theoretical concept, sometimes the experimental concept too, was actually discovered. Every field theory book you ever read introduces spontaneous symmetry breaking via magnet. Well, hello. I mean, the magnets are typically lattices. Ferromagnets certainly are, and in what I'm going to talk about in these lectures, that's certainly true. And there's one really important moral, again, very relevant to these lectures, is if you can compute something exact on the lattice, well, when you take a continuum limit, if you do field theory, and field theory is a great thing, it stays exact. I mean, if you do something exact on the lattice, you can still read that up there. Yeah. Well, you will be in a sec when I move. So CTM is continuum. So if you compute something on the lattice and it's exact, it'll stay exact if the model has a continuum limit. And, there's always this things about, mathematicians want to be rigorous and all that. When you're doing things on the lattice, quite often what you're doing is rigorous. It's a calculation. It's at finite size. There are other difficulties, but one of the main difficulties in trying to make contact with mathematicians is about the continuum limit. So if you want to start with field theory, well, just defining what a field theory is a really difficult mathematical problem. But if you're doing a lattice, this is often a well-defined problem. And the difficulties in the limit. Now, we physicists are happy to just assume that limit exists. So that will be the spirit of these lectures. Difficult.
Previously one said, mathematicians do things rigorously, whereas things
Vigorously, yeah. Well, we're yeah. Well, I will be vigorous. Yeah, I'm already working up a sweat here in these slides. Anyway, so and in particular, we sometimes can calculate things exactly on the lattice. So sometimes, of course, we do things perturbatively. But the things I'm going to tell you about in these lectures are almost always exact. So we get exact numbers out. And so if you take a continuum limit, well, it's the same number. Again, we don't prove that that's the limit. There's some very few cases. Actually, for the case written on the next board, there are rigorous proofs. Okay, so that's the philosophy of what I'm doing. So now, any questions or wisecracks, now's a good time to make them while I'm still being general. Okay, good. So let's now move to the next board and talk about the icing chain. So if you want to move this over, we'll talk about this. So I wrote this down in advance to save a few seconds. So this is going to be the canonical model, and I'll tell you in a second why I'm interested in it, but let's just define it first. So we've got a chain of two-state systems. We've got Pauli matrices acting on each of the two-state systems, and this is the typical notation to denote Pauli matrix acting non-trivially on that site and then trivially elsewhere on our 2 to the L dimensional Hilbert space. So the Ising Hamiltonian, so I'm going to do things almost entirely in quantum language, although pretty much everything I say can be generalized to classical systems. So we have an operator sigma x, and the usual basis for this flips a spin. So the Hamiltonian then is the sum over all the spin flip terms with a coupling T. Then we have a nearest neighbor interaction. So this is in many ways the simplest model of any sort of condensed matter system, a magnet. So depending on whether you make the sign of this coupling J positive or negative, makes it a ferromagnet or an antiferromagnet. We'll see soon, in fact, later today, for what I'm going to talk about. It doesn't matter whether it's a ferromagnet or antiferromagnet, the things I'm going to say. So this will either align the spins or anti-align them depending on the sign of J, or prefer to. So now, let me say what I'm going to do with this. So in 1941, Kramers and Wannier derived, and again, rigorous, a duality in this model. And I say they did do this model, they just didn't say it. They did a more general problem, which is the two-dimensional classical Ising model. But this you can obtain as a limit of that. I won't explain that unless someone wants me to. But they derived a more general thing. Also a thing I know, if you look at the paper, Kramers was under Nazi occupation when they wrote this paper, which is even more remarkable. So they derived a duality, so I'm going to explain to you today. This is the topic of today's lecture. Okay, so to understand how this duality works. I'm going to do it actually, there's a bunch of ways of doing it. I'm going to do it in a way you probably haven't seen. So those of you who think you know this like the back of your hand, well, maybe you do, but maybe I'll surprise you and do it in a slightly different way. So, okay, I'm just going to write this now in a slightly different way. And so I'm going to write just exactly the same Hamiltonian, but now I'm going to write it like this. Well, let's be obvious. We're CK, so there's an even and odd effect. Let me, can you still that doesn't come through very well, does it? All right, I got to write, let me get a different. Yeah, let's use the blue, it's better. Yeah, sorry, is anything need, ask me if anything is too hard to see up there, ask me. Right, so I'm just literally writing the same Hamiltonian. Let me rewrite it so it's better. Where's the, what did I do with the eraser? So now these k's, notice there's 2l minus 1 terms here, so this has to go to 2l minus 1. And then C, we have C2j minus 1 equals tj. So for odd k, so this is odd k, we have that, and then I guess h sub 2j minus 1 would be sigma jx. And then likewise for even k, we would get, sorry, there's no j here, okay, and then h2j equals. All right, so I've done nothing at the moment other than rewrite it. But now I'm going to do something interesting, and then this is, so I'm going to rewrite the Hamiltonian, oh, sorry, let me, okay, well, let's keep that. H sub, sorry, let me make that a small h, just because I don't want confusions. Because I'll slip and write that as a small one later on. So that's just a small h. Right, so, but now I'm going to talk about what now gets called the free fermion bond algebra. So those, again, many people here know this model very well. You know you can solve it by writing in terms of fermions and all that. But I'm going to explain how to approach this model and not say a thing about fermions, free or otherwise. So I'm calling it the free fermion bond algebra to remind you that there's some fermions lurking there. But you don't need to know anything about fermions. You don't need to know what a Janot-Wigner transformation. And it's the fact that these H's satisfy a certain algebra. And the algebra is the following. So they commute if they're far apart. That's obvious. They anticommute if they're next to each other. And they square to 1 on a site. So already you notice something simple by this rewriting. Notice even odd doesn't matter. They satisfy the same algebra independently of whether it's even odd. That's a hint of what's going on. And then something even more important happens. So I'm not going to prove this, but you take my word for it. You can compute exactly the spectrum of H just from this algebra. So you trust me, and actually I could do this, this isn't known. So Baxter once wrote a paper called The 399th Way to Solve the Ising Model. I don't think there's that many, but there are a lot. And many of them really interesting because they highlight a different aspect of the model. This might be the 400th, or at least I never saw it in the literature till I wrote it down a few years ago. Certainly experts knew this, but I never saw it written down. So you can compute exactly every eigenvalue of this Hamiltonian just by manipulating this. So I could tell you how to do it, but that would take me 15, 20 minutes, and it's not about non-invertible symmetry, so I'm not going to do that. Okay, and by the way, and that method generalizes to some other models, this bond algebra type method, if you wish, things that I've spent some time on called.
If I multiply the so-called even terms around the loop, you will get
I haven't talked about boundary conditions. I will talk about this. I wrote down this Hamiltonian, and I can make it periodic too if you want. Doesn't matter. I can make it periodic if you want. And the statement I said is true, that I can compute the spectrum of the Hamiltonian. I don't ever need to write down fermions. I actually don't ever need to write down what these operators are. The calculation is utterly complete. There's one slight caveat is to do this calculation that I didn't say, that you have to introduce, if you do it for this one at least, you have to define an extra operator that lives at the edge. But I mean, that's just a definition. But you don't, so yeah. Anyway, so all right, so I'm just telling you this is a fact, and let's go somewhere with that fact. This distinction I made. So I could write down another Hamiltonian. So let's call it H hat. Sorry, let me write it. Look at my notes to make sure I write it exactly. And I'm going to define it in a certain way. Let me, all right, yeah, so let me draw a picture before I write H hat. What I do it? There we go. So, okay, so we're living on these sites here. So I'll draw this. So these are sites 1, 2, 3, 4, up to L. Okay, so now I'm going to define another model on not the same lattice, where I'm going to draw the sites here, and just to hopefully avoid confusion, to emphasize that these, you'll see in a minute why I did this, live on these half-integer ones. And so then there's actually one more site here. This goes up to L plus a half. Okay, so I'm going to define another Hamiltonian, which I'll call H hat. And that's oops. Okay, and oops, forgot the J hat. Okay, this is another Hamiltonian on this other thing. That's not a typo, that's 3 halves, and only runs to L minus a half. And you see, I made it so there's exactly 2L minus 1 terms in that one. So again, I can, well, of course, they're Pauli matrices acting on these. That's why, yeah, exactly. I'm defining it. This, at the moment, this is a completely different model that I've written down. I'm doing this because I want to make the statements of duality absolutely clear. One of the reasons I'm doing it this way is because everyone, we physicists have this tendency, shall we say, like mathematicians, this is one of the bad habits we got from mathematicians, is that every time we understand something, we then say it's trivial. Whether or not it actually is trivial. And the duality literature, it's filled with things like, of course, I'm sure I'm completely guilty. You can look at, I'm as bad as anyone. Of course this is true. And until 2 years ago, no one had the foggiest idea this was true. And the original paper is completely incomprehensible. But nonetheless, it's now completely obvious because at least a few people somewhere on the planet understand this. But anyway, so I'm doing it this way because I want to be absolutely clear about what the statements are, because they've gotten muddled yet again. And I'll give you an example in a little while of one muddling. Right. So then I write this thing exactly like I decompose the other one. Again, I said there's 2L minus 1 terms. And so I won't write out those definitions. Hopefully I was clear enough on that one. So it's exactly just the same way. It's still up there. So do exactly the same thing. You just basically put hats on everything. Okay, but well, maybe now you can see where I'm going. It's the same number of terms, same thing. The HK satisfy the same algebra. This free fermion bond algebra. So I'm making up. It's the first time that abbreviation's ever for the same free fermion bond algebra that's on the other board. Just put hat on everything. And I just told you a few minutes ago that you can compute exactly the spectrum of this just from this algebra. And I should be precise now when I say compute exactly the spectrum. So what I mean by that and this here, this means all the eigenvalues. Getting the multiplicities of eigenvalues you can do, but that's a little subtler. So when you then now do the same calculation here, said it only follows from the bond algebra, what you find is H and H hat possess the same eigenvalues. Is that oh geez, oh no, God, what a disaster. Okay, sorry. But they say the multiplicities, you have to do the questions Eduardo was complaining about a bit, meaning worry about the boundary conditions and things like this. The difference. Well, yeah. Right, good. No, that question is the right side. Good. I will answer that momentarily, but any other questions? Because I've already thrown a lot of stuff out there. All right, please interrupt if you can. Right, so at the moment, we've just got two models. One defined on, this is L+1 sites, with this Hamiltonian with these couplings. We got model 1 and model 2. So the difference is the number of sites? Yeah, they have different number of sites. Other things, yeah, good, I'll start taking this out. Like, for example, actually, let me say this now. This model, model 1, has what we would call free boundary conditions. All right, so notice we've got a spin flip at every site. There's nothing like a magnetic field or anything special at the boundary. Just, it's happy, you just stop the system at the end. Again, this thing just interacts nearest neighbors. So this would be, say, has free boundary conditions. So now let's look at this model. So I said this isn't a typo. This starts at 3/2. So this spin, notice 1/2 appears here. So it's part of the system, it interacts, but there's nothing that can flip it, because I left this term out. And so this is what's called fixed boundary conditions. So these are two different models, but by this bond algebra thing I asked you to trust me on, if you did the calculation using fermions, trust me, you would find it. You'll find that these things have exactly the same eigenvalues. Some function, some set of eigenvalues with t and j. We can do this calculation because of free fermions. Is that, Horacio, is that what you were asking? Huh. Yeah, right. So they're not the same model. Sorry? Did somebody? Oh, okay. Yeah, no, they're not the same model. And this is often, when I was alluding to these confusions that people make because they act like everything obvious, this is something that often got lost. We wrote, I don't know, a 60-page paper where I tried to make, in 2016, tried to make all this clear, and then certain people who I may name later confused matters again. But this is, I think this is the right way to think about it.
Yeah, but if you work with periodic boundary conditions, they have the same number of sites.
Yeah, but they're not the same model.
They're not the same model, I guess.
Even at the self-dual point, unless you do, I'm going to get there. I'm going to explain that point very carefully. Good, please, any more questions?
So is this true for any L, or it has to be at the...
Anyhow. I mean, this L and L, this L and L plus 1, but any L, absolutely, yeah. No, once you set this up, it's really nice. Yeah. Yeah, we kind of, I mean, that's in the details. You'll find the eigenvalues, of course, will depend on L, not surprisingly. Just like if we did periodic, it would depend on them, 2 pi over L's and things like that. And here they're standing waves. If we, so I haven't done the calculation, but if we worked it out, we would. Good. All right, so good. Sorry? No, we'd be different. Because among other things, we would have an extra term in here. Right. So we could, if I started with 1/2, I could then find another model here, but I'd have to add something else in there. That's a good question, but no, so it's, so these models, well, to use the word, are dual to each other. So if I changed this model, I could find another model of the other type that's dual, but not to these. The spectrum would be different, or I should say the eigenvalues would be different. Good. Oh yeah. No, I haven't talked. Oh, sorry. Yes, good. Thank you. I didn't say a key point. Yeah, so I got distracted in this whole thing. But yes, so here's a key point. I said the spectrum's the same, but in one case, thank you. In one case, I wrote, well, the spectrum of this one obviously depends on T and J and L in some way. L is the same for the two models, but this one I wrote T hat and J hat. So let's look at this. So yeah, I quickly said, oh, you can do the same thing with the even and odd here, but that leaves out, let's actually, let me leave that up. Yeah, so good, let me write that out. So when we do this, the bit that I didn't write out, so what happens here? So the analog of this, so for odd k, we have ck hat, or I should say, I wrote it with odd. Ck hat is equal to j hat. Because I'm starting at the end, so this is why I drew the picture like I drew. So I'm starting at the end here. So the first term in this, notice, is here. So this is, if you wish, so let me draw. So this would be That's visible, okay. So this would be T, the T term, and then there's a J term that couples those two, and then there's T. So that's why in this bit, we started at T. This is the odd, so 1, 2, 3, 4, and so forth. But now let's do this one. Well, the first term, as we've made a point of, this term isn't there. So the first term that happens is here. It's J hat. The second term is then the spin flip acting on 3/2 site. And then this one's J hat. So when we do this, for odd K, meaning the first term you get, we'll see K as J hat, and the corresponding HK hat would be sigma K minus 1/2. Okay. Is that legible? Yeah. And then likewise, the even K. So CK hat is T hat, and HK hat is equal. K minus 1/2. No, K minus 1/2. Okay, so we've compared the two, and now in this correspondence, so I said find A have the same eigenvalues. That's correct, but we must identify So we've identified the terms the other way around. So in other words, you get your formula, you do this calculation I didn't do, you have an answer for T and J and L, and then for the other system, I plug in the opposite eigenvalues. So that's the way it is. Yeah. Right, so, okay, yeah, no, so, okay, we get a formula for the eigenvalues, not for their multiplicities, but all the different eigenvalues in the spectrum. That's a function of T, J, and, there's some integer label. And it's right in terms of T and J. So if we did the calculation for the other model, we'd get exactly the same formula that lists all the eigenvalues. I could write it down for this model if that would be helpful, if people want me to. But the key thing is I get the same exact formula, but where T is replaced by J hat and J is replaced by T hat. And again, it doesn't say the multiplicities, which is absolutely crucial. But so it's just a formula. You can write, because this is free fermions at the end of the day, so that it looks like free fermion for us. Good, please ask if there's more. I'm going shockingly quickly. I wasn't expecting. This is good. Okay, so let's do some physics. That was in the title of my talk. So this is an amazing result. So before I'm going to explain, the rest of the lecture is going to be understanding this duality. And so this is what's called Kramers-Wannier duality. And again, sorry. Okay, that's not so bad. So Kramers-Wannier duality, and what this says is the model at Tj as the two couplings is not equivalent. Again, you'll see, they're the same model. They're equivalent. They're not the same model, but is related to, it's certainly true, in the sense I've tried to say, to the model with J hat and T hat. So let's say the Ising model in 2D classical or 1D quantum is related to the model there. And so let me kind of elaborate with that now. So I'm going to kill this, but I'm going to keep this picture. Yeah.
Since I worked on this when I was a kid,
Yes.
and I have some friends. There is a global difference between them, but at the local level they are the same.
I'm going to get to that. Trust me.
They are not? Or they are
I've been trying to be very precise. And my precise statement, that's why I said is related to.
You work in the thermodynamic limit, okay, which is what sensible people do.
Did you hear my introduction, Eduardo? Did you hear my introduction? Yeah, well.
So you work in the thermodynamic limit and you look at correlations of local operators.
I understand.
You can relate one is equal to the other in the thermodynamic limit.
I understand. That's why I use the word relate, not equivalent.
You mean up to boundary conditions?
I said relate, and I'm going to try and explain this carefully. I'm trying to be precise too. That's why I'm being to the point of pedantry sometimes, but it's a try. So let's look at. I'm going to try and talk now precisely what this means to be related. So let's I put ground in the title because looking at ground states does this. So I erased the other model. Hopefully you remember. So that's still the T hat is J. So up to boundary conditions, they're kind of the same. And so let's do some physics for a minute. So physics of H. Just to be concrete, we're going to talk about physics of that thing. So now, if we look at the ratio of the two couplings, so if we go T over J to 0, so basically just forget the flip term, and the model is ordered. And so it has two ground states. So all up and all down. If J's, this is if J's less than 0 in my conventions. And if I took J greater than 0, it would be up, down, or down, up, down, up. So still two ground states, the antiferromagnet. Okay, so in this case, we got that. So if T over J now goes to infinity, there's only one ground state. Which is, you can think of it in a bunch of ways. It's the eigenstate of sigma x. It's an eigenstate of sigma x. I should have, will people be unhappy if I do that? Just physics is all the same. Anyway, so there's one ground state, which is the eigenvalue sigma x equals plus 1 on each site, which, if you think about it for the second, is proportional to the sum over all states in the z diagonal basis. Okay, but the key thing for today is 2 and 1. But now, the other chain I wrote down, the hat one, I erased it because we ran out of room, but it's schematically illustrated here, is exactly the same. So if we do T hat over J hat goes to 0, we get the same thing. And if we get T hat over J hat going to infinity, it's the same thing. But I said, over here, there's the same eigenvalues. But when I exchange T hat with J, and blah, blah, blah. So we've said something very strange. I'll put that back up later. We've exchanged, where's my blue? Sorry?
In one case, T hat over J hat has to go to infinity, the first case, 0 is 0. Since you flip, I guess.
No, no.
Well, if you take just if T hat is J
No,
and J hat is T, then they get split.
no. So I should have written, I've written, let me rewrite the H hat. H hat was T hat sigma X plus J hat sigma Z sigma Z.
But T hat is J and J hat is T.
No, I've got two models. I said they have the same eigenvalues if this is true. I did not say the two, I'm not setting those things true. No, but this is the crucial point. What I'm going to say next is what we've said is this duality, this Kramers-Wanier duality, maps a model with say two ground states. So that's T over J goes to 0, or T hat over J hat goes to 0, to 1 with one ground state, which is the model, so depending on which regime you're in. So, yeah. Sorry, I couldn't hear the question, please. Yeah. Yeah, that's right. No, it's... Yeah, well, yeah, so limits like that, this is why I put arrows, not equals. Yeah, so even for 0, where, of course, I can set t 0, but I don't want to do that. I just want to make j really, really big. Yeah, no, yeah, right. Yeah, you can get very confused by doing things like that. That's why, yeah. Good, is there somebody else? Yeah. Well, yeah, I mean, so the point being is they're essentially the same model, modulo boundary conditions. But when we do the map, so, okay, good, yeah, that's maybe a good way to say what, emphasize something. So what we're saying is the duality here that we talked about is a map, so this is related. So let me erase my is related to and make a more precise statement. So it relates a model. It says the spectrum. So, sorry, let me say the eigenvalues again, with this emphasis that it does not say the degeneracies are the same. The eigenvalues of Ising chain with free boundary conditions in the ordered phase are the same as those with fixed in the disordered, and vice versa. So that's the precise statement. So yeah, you can get confused, but I hope my pedantry has at least illuminated some of it. Yeah. No, so what it says, in fact, yeah, so I talked about the extreme limit. So say we deform away. Yeah, okay, so these things are not the exact ground states. But until I hit a phase transition, these stay the ground state. I mean, that's just a definition of what we mean by phase transition. And you have two ground states. So throughout, even for, now there's a point where t equals j. That's the self-dual point, and I'll get to that in a bit. But no, so this map will always be 2 to 1 or 1 to, well, not 1 to 2. And I'm going to try and, yeah, good. I still have time to get that today, I think. Yeah, okay. I'll still have time to maybe illuminate a little further. So it's true everywhere. It's not just true in some limit. And the degeneracies, in particular, this 1 to 2 or 2 property, that doesn't change. I mean, because it can't. I mean, that's one of the beautiful things about this. It can't change because, that's not 2 to 1 is not continuously deformed to anything other than 2 to 1.
Well, I have a philosophical objection.
I'm considering a finite system.
Finite system with arbitrary values of t and j, there is a theorem that says the ground state is unique.
Yes.
So there is no degeneracy. On the other hand, in the thermodynamic limit,
Okay, fine. All right. So apparently, yeah. Okay, thank you. So Eduardo's informing me that I'm not being pedantic enough. So, you want pedantry. I am your man. Of course. In a finite system, in this particular case, at any rate, there are not 2 ground states. There's only one. Because there are finite size, exponentially small corrections. So when I say 2, there are 2 states in the system that are exact. However, we can concoct systems where the states are exact.
sorry for that.
Right. Anyway, any more pedantry? I like this. I mean, we can. You don't know what I do on an average day of my life. I mean, this is fun for me. Right. Any other things we wanted to say? Okay, good. Sorry. So this really everything I said was pretty well understood in 1941. But there's something, we do learn something new occasionally. And actually, I want to highlight some papers because in all the hype about non-invertible symmetries, as various wheels get reinvented, it's really the following authors' work. If you read your average string theory non-invertible paper, do not mention, even though they really had a key thing. Okay, so physicists were content with this, of course, lots of confusion then as now over what this meant. But what these guys did for the Ising case in the late 90s, I think Schutz was, actually, I wrote them in the wrong order. Schutz was the first, I think that was like 93, I think them, and I wrote them in reverse chronological order. They said, well, what can we, how can we understand this a little better? And so what they said is, I'd say in modern language, what they did was the following. They said, let's look for an operator D that maps, so D maps the Hilbert space, is an operator acting on the Hilbert space of, let's see, the way did I do it? So D is acting, I want to make sure. It's right, so D acts on the, did I write this backwards from the way I wrote it there, but I want D. Just to avoid destroying my conventions later on, I want to make sure my conventions are. So D is going to act on. No, so this is right. So D acts, what? D is going to map one system, one Hilbert space to the other, and I'm confused about it. Right, okay, no, I'm sorry, this is right. So D maps the Hilbert space of, so I'll call that Hilbert space of the hatted system to the Hilbert space of the original system. Right, so you think about this. So we have a Hilbert space, this is the hatted system. H hat's acting in the hatted system, and then we map it over to the other Hilbert space. In this case, we first do the map from the hatted Hilbert space to the original one. And D dagger does the other way around. So this is an operator. So you can say this is like a symmetry. It's commuting with the Hamiltonian, but of course it's not, because it's it takes one Hilbert space to another, but it says that let's talk about this one. You act with this Hamiltonian, you then map over to another Hilbert space. This says first do the map and then act with the Hamiltonian, and you get the same answer. So, of course, all this stuff I've told you hints that such a thing exists, but as far as I know, nobody ever actually wrote the thing down. And so it maps this thing maps eigenvalues to eigenvalues. Well, that's the same, I should say, the same, max a given eigenvalue to the same eigenvalue. That's what I mean by that. Okay, so they just wrote it down. I mean, it's once you have this idea in this particular case, it's not super hard to do. It takes some work. It's not trivial. But let me write down the answer. Do I still need that thing? Let's leave it up. Yeah. Yeah. So, no, sorry. Yeah, so I never make the swap. I never set T hat to be J and J to be T hat. What I say is if you do that, then you get the relation between the eigenvalues. But T hat, J hat are parameters there. It's just a relation between the two, spectrum of the two when you make this identification. So what this really means is, right. Sorry. I just realized I answered your question wrong. Right, so this, yeah, so this is, so right, so let me say, let's do it this way, right, so, yeah. No, good, thank you. So this would then be saying set T equals J hat with T hat equals J. Yeah. Yes, okay, yeah, good. Yes, no, thank you, that's a crucial point. So yeah, so I'm trying to never set that, but yes, so from now on, when I make statements like this, implicitly I say with this appropriate identification. But yeah, thank you very much. Good. No, it's for these boundary conditions. So if I change the boundary conditions, then on one, then I would have to change the other model as well. Yeah. And so in particular, I can do all this for periodic boundary conditions. I think this is actually easier to conceptualize what's going on. And in a little while, when I've hopefully clarified things a little bit more, maybe it'll be a little clearer to. But no, that's absolutely important. We're very much stuck with. If we want to do this map, we have to one of the things, again, that people confuse in the literature is they don't, often it doesn't really matter what you're doing, so you can just ignore that. But if you really want to be precise, you have to specify exactly what you mean by a boundary condition. All right, good. So they wrote down the answer for this D. And so the way it works is the following, is we write... So D now, the way I did it, D is acting, right? It acts on this one and then gives you that one. And it's the following. So let me draw this now. Let me try black again. See if I can get black to work. So what I'm going to draw it as things that just act like that. So D is a product of some weight that I'll write down in a second that say just depends on the values of the spins there times 1. So it's really nothing elaborate. It's a product of all of these things times the one that does that and so forth. So it's the product of all of those things. So these are the matrix elements of D, I should say. Okay, and then the answer is the following. It's really simple. If we label the two sigma z eigenvalues, so let me just label the sigma z eigenvalues as equal to +1 or -1, and then the same for sigma j hat. So again, these are + or -1. And then they just depends on these two values, and I'll call, if that's sigma. So this is sigma in this model, this is sigma in that model. It just depends. 1/4 times -1 to the sigma -1, sigma hat -1/2. That's all. So what this is, it's easier to say this in words. This is equal to 1 -1 if sigma equals sigma hat equals -1 and 1 otherwise for the other three cases. And it's got this stupid, times this stupid 2 to the 1/4. Right, 2 to the 1/4 is the hardest part. Just to get a sensible get a nice normalization, you have to put that in. So that's it. That's what these guys did in various versions, right? They did more than that, but that was the outcome of that. So there's this operator that, again, notice doesn't depend on T. So that's a good sign that something deep is going on. It doesn't depend on T and J. Just basically + or -2 to the 1/4. So let's look at and so actually you can check. They show you an even stronger statement. I said that, but because this thing is local, or product of local things, so it is definitely non-local. It stretches across the whole system, but it's a product of local things. The statement is even stronger. Oops. It's okay. Again, under that identification over there is implicit in all of it says. Yeah. I want a 4. No. No. Oh, to 4. No, I want this. So let's do it. So if either one of them is 1, it vanishes, which is I want. Oh, you're right. Thank you. The mistake you make when changing in your head from 1 and 0 to +1 and -1. Yes, thank you. All right, it would have been trivially otherwise. Good. Any other mistakes? So it's an even stronger statement. So these things commute locally. Or, commute is the wrong word. Map locally. Which turns out to be very valuable for things. So I could even do this for random couplings. And again, one of the things I'll come back to in a bit, but with periodic boundary conditions, people like to have periodic boundary conditions because we like periodic boundary conditions. And so people often confuse duality of having something to do with translation invariance, but it has nothing. I'll come back to that with it. Nothing to do with translation invariance. You can mix it with translation invariance if you want. Right, so that's the answer for that. So that's pretty cool. But then something interesting happens, and then it's going to shed a huge amount of light on this issue of this 2-to-1 thing that I talked about a little while ago. So this 2-to-1 thing, now really we can come, let's not do that one. Let's do, where's my beloved blues? Here's my beloved blues. So what we find, now let's do this twice. So we act with D, and we act with D dagger. Well, we know something funny is going to happen. So you can just work out, trust me. That's right, this isn't a school, so I can't say go home tonight and do it, but you'll be a better person if you do. So what happens, you do this twice, and it's not, duality is a terrible word. It's not dual because it doesn't come back to itself. You do it twice, so we have to do dagger, so we map up and then we map back down just with the Hermitian conjugate operator. Again, you can write down everything here as matrices, so there's nothing subtle about that. And so you find where this operator, F hat, is the spin flip operator. So we're in the hatted model, so we would do J hat equals 1/2 to L plus 1 over sigma x. So this just flips all the spins. Still legible, yeah. So he comes back. So, and then likewise, if we did it the other way around, so start by acting on the original model's space, we get this, where just the obvious analog, J equals 1 to L, so we next check. So now what's going on is starting to emerge, which, and answers Eduardo's last question, which is the following. So we can see now this maps onto a projector. That's the reason for this 2 to the quarter, to get nice factors here. So if this operator, well, let's do that one, annihilates half the states in the system. I'll write this out a little more explicitly in a second if that's not obvious, why that is. But it's kind of obvious. This thing has lots of 0 eigenvalues. It's 0 eigenvalue on half the system. So you can go back and check with this definition we made, and you see this operator D dagger just literally annihilates half the states in the system. Well, or half the Hilbert space, if you will. You write basis elements for half the Hilbert space. Gets mapped. So this is the very, this is so non-invertible, right? Literally half the system goes to nothing. And in either direction. So this explains the 2 to 1, and this answers Eduardo's question, which is the fact that, yeah, we don't map between 1 to ground. So we map to the linear combination of 2 states. So let's go through this in particular. So if you work out the states, so I actually did this, so again, another exercise to the student. This one's even easier than the one I did. Okay, we can kill that now, I think. You can just see now, if we act on these almost ground states, this state will go just to the combination. So this is in the hatted system. I'll just put hat there to remind you that's spins in the hatted system. Just goes to the combination. So it's just a definition. You take this thing, you work it out. It's, again, super instructive to just do it, to see what's going on. And so, again, this is the sum of all states. This is the state with eigenstate of sigma x with all the sigma x. But here now we do the same operator on the minus 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 state, and we get the same thing. Just do it. Just an operator, just an 8x8 matrix, or not even, sorry, 8x4 matrix. And so what you see now, well, so D annihilates this linear combination. And then you see in general, basically, if you take the linear combination of something minus its flipped version, D annihilates it. And then D, the sum of the two, gives you the sum over all configurations. Properly normalized times some normalization. So it's sort of mapping between ground states, and this answers Eduardo's thing because with this case, with these boundary conditions, this one's the actual ground state. So this is the one that maps to the other ground state. Not surprisingly, this thing, which is exponentially higher in energy, just maps to nothing. It's the way it is. Now you can muck with boundary conditions and make it the other way around. You can map one, so you can make it so it maps the other half, but then you lose one half. But then you're changing the model if you muck around with boundary conditions. So good. Where am I on time? Oh, good. Okay. Still got some time. Good. Yeah. No, that's perfect. Oh, good. Yeah. Oh, good. Good. I think I'll have time to actually do what I want to do, which almost never happens. Right. So now, okay. So we can do this for periodic boundary conditions, and then we don't change the number of sites. But because of this relation, well, either one of these, things happen. And again, it's a map between sectors. So you think about, you're taking a sector of the theory with periodic boundary conditions. So the one with this is positive. So this maps sectors of theories. Okay, so you look at this sector in this theory, and it maps to that sector in that theory. The one where, say one in this case, 1 plus f equals 1 goes back and forth between 1 plus f hat equals 1. And the other sectors just get killed. Now, if you want to change that, so now with periodic boundary conditions, say what you can do is you want to start, I want to map, I want minus, I like minus. But you find, when you work it out, you can map it to a model, something in the other model. However, it has twisted boundary conditions. So it maps to a different model. You have to do something on the boundary. So in the old days, people knew this, but I think until this formulation by Grimm and followers, there wasn't a clean way to understand. You could just do this ad hoc. So you twist the boundary conditions. So it's a map between sectors, and if you include all the twisted boundary conditions, you can map any sector you want to any other one. But you can't just say, I demand a duality map from model 1 with my favorite boundary condition to model 2 with my favorite boundary condition. So like in the example I gave, it maps free to fixed. That's the way it works. No. So you're saying, so in fact, all right, so you prompted me to tell a story I haven't told in a long time. So I gave a job interview at Harvard. And I made the mistake of reminding David Nelson in this interview of something he said in class once. I was a grad student there. And he said, boundary conditions never matter in theoretical physics, what Eduardo just said, except when they matter. And having spent a good chunk of my life, I pretty much argue that they matter a lot. And they certainly matter if you want to understand what the hell you're doing in this problem. So. Yeah, I know. That's what I just said. There it is.
I think this has always been clear. It was clear to me when I wrote my paper.
Yeah, because Eduardo, you're smarter than most people, so you're smarter than me. All right, let me. No, again, as usual, the experts understand, and then the expert thinks. So, okay, good. Let me give you an example of a paper that this is being recorded, so I should be nice. What do I want to kill? Okay, we can kill this. So where things got muddled again recently, so I said I tried to be very pedantic, and we wrote a. So I should credit my collaborators with this. So we did a lot more in the paper. Everything I've told you today was known forever, but I wrote a paper in 2016 with Dave Asen and Roger Mung that actually doesn't do it this way, but we said a lot about the icing thing, but we did try and be pedantic about this. And in particular, one of the points we tried to make was that the duality has nothing to do with translation invariance, but it gets muddled. And so there's something reasonable you can want to do. So we can answer the question, can we make duality a symmetry? So I mean, you have this DH equals HD. No caveats, right? Same H, same coupling, same everything. And so here's how you can do it. So first of all, you take T equals J. That's pretty obvious. Then you can ignore that caveat that I had neglected to say before. Okay. You take periodic boundary conditions. Okay. And then you have, okay, so far that's fine. Both as Eduardo says, who cares about boundary conditions, so that's fine. But here's something you have to do that's, that is subtle. You have to relabel the half-integer sites by integers. That sounds fine. We're allowed to do that. But in periodic boundary conditions, there's two ways of doing this. I can label 1/2 by 1, or I can, whatever. And so you can take j hat equals j plus a half, or j hat equals j minus a half. Because it's the same model, I got to do exactly the same. But see, so then what happens if you do this? So again, all this still applies, so it's only going to map sectors to sectors. But there's something a little bit weirder here. When I do this twice, you don't just get 1 plus f. You get 1 plus f, so d squared, it's the same system, so it's self-adjoint. D squared equals 1 plus f times the translation. Depending to the left or the right, depending on which convention you chose. So it's not a convention, it's actually, well, you pick a convention and then that tells you what direction your translation is. This is fine, it's perfectly legal if you want. But to me, it's a very special case, and you lose a lot of the structure of duality. If that's what you want to do, you have to. If you're okay with all those things, if you're okay with restricting to the critical point, okay. Yeah. Oh, sorry. Say it again. Oh yeah. So this would be with periodic boundary conditions, because then they're the same size. So then you would have this picture here, right? And for periodic, so this was L1/2, we would identify with 1/2 for periodic. Was that the question you were asking? Yeah, okay, good. Yeah, so they're the same number. But again, so yeah, I should have gone to this. I should have said that before. Go to this picture. Whether I again decide to shift that this way or the other way, I can do whatever I want. That's a convention, but it then affects the algebra. Can I? Yeah, right. So not in this case, right. So in the original case, yeah, you can make, in fact, if you remember, I guess it's long gone now, we had Yeah, this can go. Remember we had this, I wrote it like this, or something like that, or 8 little h. Right. And I can make C's to be whatever I want, just as long as in the other model I put the appropriate C. But yeah. No, so this is okay. Yeah, this is a good opportunity. Yeah, keep asking questions and then I can start next time with, I have about, I think 10 minutes more of stuff, but if people ask questions, that's fine, I'll do it next time. Right, so translation on the lattice to translation in the continuum is a really subtle thing. And in fact, it's, if you've read Natty Seiberg's thing about eminent symmetries, this is part of that story. The point is just, so it's been known to condensed matter people since, at least since the 80s and probably before, that if you have a lattice translation, obviously that's a symmetry, and pretty obviously that's going to go over to translation symmetry in the continuum. But there's a catch, because if you do things like in an antiferromagnet, or something more complicated, so that means I have, how much time?
15 minutes.
Oh, 15, wow. Okay, maybe I will get to the other stuff. So if you do, say, an antiferromagnet or anything where the unit cell is bigger, you don't know how many lattice sites you have to translate in order to get the continuum translation variance. So in antiferromagnet, it's often 2. So the continuum translation. But then there's an interesting question. Well, what happens to the translation symmetry of the lattice model? It's a perfectly good symmetry translating by one site. Even in an antiferromagnet, it commutes with the Hamiltonian. It may be spontaneously broken, but it's a perfectly good symmetry. And what typically happens is it becomes an internal symmetry. And then these things, you can get anomalies and all that. And it's so on the lattice, you can see everything absolutely concretely. The subtlety goes now when we want to identify the lattice symmetries. And this, for example, is the famous old Affleck and Haldane paper where they explained for the antiferromagnets how to do this mapping between this and conformal field theory. And it's absolutely essential that you get this right. In that case, the answer is lattice translation becomes there, and then the lattice translation by 2 becomes translation, and then lattice translation by 1 becomes an internal symmetry. And that leads to all sorts of interesting subtleties. But is that, yeah. So you have to be super careful when you're making this thing. So this is a lattice statement, and then you have to figure out in your field theory limit what that corresponds to. I think here, in Ising, it will be translations there, but if I did this for the XXE or Heisenberg spin chains, it's not. It's something more complicated. So you gotta be careful with this kind of stuff. There was something over here, I think. Yeah. Yeah. No, well, so the map is 1-to-1 within a sector. So the key is once you, if I restrict, so I wish I hadn't erased this, but remember we had D dagger D equals 1 plus F, and that's right. And then now let's do the self-dual case, so it's D squared equals 1 plus F with all the boundary conditions and all that. So when you do this, now say I go to the sector F equals 1. Or I'm doing curly F. F equals 1. Well, then this is just equal to 2 in that sector. So this is now invertible, as long as you stay in that sector. So it's invertible within the sectors, and it just kills everything else. So this is the way you solve the problem of this 2-to-1 bit. You just throw out, it's the nicest way. You just throw out half the stuff and forget it. Yeah.
You can also say that that operator is not invertible because it has the most states.
Yeah. No, obviously, yes, right, exactly. But I'm trying to say, it's really not invertible. It throws out half of them. I mean, that doesn't just, often we find, you put the little prime in your instantons, your Dirac determinant, fine, throw out 1, 0, half of them. Yeah. Yeah, yeah.
interactions that we have there. But the translation, if you have a homogeneous, so the translation is another operator.
Yeah.
So it's not the usual translation operator.
No, it's the usual translation. You do duality twice, and you get well, you get this 1 plus f, you know, but okay, we project onto that sector. So no, sure, no, of course it's a symmetry. It's perfectly a symmetry. Because we're not. Oh, this does. So you can't do this for the inhomogeneous case. Oh yeah, yeah. So right. So this was before. So it must be completely homogeneous. Yeah, good. Yeah, I think I said this before your question. So that yeah, I should have amended it. Yeah, good, good. Any more? Or do I do a few more? There's an yeah, sure. Preserves the norms of. Well, I can put 1 over square root of 2 if is that what you're worried about? The meaning of the 2 is there's a nice local way to define this operator such that this is true, I think. It's literally just a definition. I can call D something else if I want. It's just when all the stuff Dave and Roger and I did in our 2 papers, we could just repeat it and then you would put a 1 over the square root of a certain thing that we know what it is, the quantum dimension of the associated operator, and define D that way. But it would just be an extra little bit you would add. And so this is the natural way. I don't want to attach any significance whatsoever. That's just easier to write this way. That's all. It's just the thing that pops out with the nice local definitions of all this stuff. Well, I think once you go to the appropriate sector, then you're free to fix normalizations. I mean, you get these elaborate the point is you get these elaborate algebras. This is simple. This is the simplest non-trivial version of that. And I think it's typical, the normalization that comes out naturally when in this elaborate setup that hopefully I'll get to at the end of my lectures, to have the identity appear with coefficient 1 is a good thing. Oh, sorry. And of course, in this normalization, then the coefficients are always integer, I think. That's why this is the natural one. I will ponder that after the talk and make sure that's correct, but I think that's correct. The coefficients are always, yes, no, that's correct. If you use this normalization, coefficients are always integer, so that's better than squaring to 1. And also it can have multiple non-zero eigenvalues too, so that are irrationally related. Good. All right. So 10 minutes or so left. Oh, it's 12:27. I don't think I have 15 minutes. Maybe I should. Did we start that late? We start that late? Because it's 12:27 now. So, I mean, I'll. Should I? Yeah. Yeah. Should I? Okay. So let me do 5. Let me do 5. I'll do it quickly, and then I'll do something quickly. So I wanted to give something slightly newer application. So application. All right, so the situation we're in is now we have this picture of the Ising model. So this is, say, T over J, and this is ordered, and this is disordered. So now something I did not say, because this requires other stuff. So the duality map, if you wish, is changing relating the physics of the 2 things, and this is the self-dual point, T equals J. Now it turns out in Ising, this is not guaranteed, but this point in the middle is critical. This is not always true. It's also not even always true that the self-dual point is a phase transition. You can get big phase transition regions, all sorts of things happen. But in Ising, this is true. Okay, but we can ask, okay, so now let's try and understand the physics. What happens when we add another parameter call it lambda, and I'll give you an explicit example of lambda. So that's going to be in this direction. So, but I want to make lambda the coefficient of some self-dual, of a self-dual term. And so what I mean by that is, so let's go to this special case that I said here. Let's go here, periodic boundary conditions, blah, blah, blah. And let's look for a self-dual term. And so one example, and the one I'll tell you a little bit of physics out, say is x, j. Oh, sorry, I'm doing sigmas in this talk. Sorry, not a quantum information audience. That's right. It's getting close to lunch, right? One of the greatest contributions of quantum information to physics is getting rid of the sigma and the Pauli matrices, but not the only great contribution. I didn't say the only great contribution, but I said one of the great contributions. Anyway, so say take this term, and this is manifestly self-dual if you add them all up along the line. So translation invariant version of this. Because it swaps, the duality swaps these two kinds of terms. That's still there, the DH equals HD. Okay, so let's add that one, that's self-dual. So what happens, so this term is irrelevant, we know from general things. And actually on general grounds, this beautiful paper in conformal field theory, and Kester, Martinick, and Schenker explains it in that language, but it was known even before that would happen. So what happens is you get this tricritical icing point. That's what TCI, tricritical icing. So if you like conformal field theories, as I do, this is some interesting thing. But then you say, well, we're on the lattice, we can just turn it up further. So let's keep going and turn up. Well, what happens here, so here, this becomes a first order transition. And so, no, so this is with this perturbator. Yeah, let me write it out more carefully. So this, we'll call this HSD. Huh? Plus this. You push yourself up to the tricritical icing. So this is at a particular value of lambda, and for this model, I even know it because I wrote a paper on it with my then student Ed O'Brien and me. 0.856. Turns out it hits this tricritical icing point. Yeah, so T, this is where T equals J equals lambda equals 1. Oh, sorry, not lambda. I said T equals J, not lambda. And then when you turn this up, so it's irrelevant if you want the RG, you flow from tricritical. So there's, again, ask me, there's a whole nice, beautiful picture of all this that is really, really nice. Oh, yeah, supersymmetry is involved. But in any case, so you can do this, but then we can ask an interesting question. What happens when you go beyond? And we're on the lattice, we can keep going. This is the phi 1,3 perturbation, if you like conformal field theory. So it's the phi 1,3 perturbation of tricritical icing with the other sign. But what we have here is something very strange. At least I would think it's pretty strange, which is order, disorder, coexistence. So there's 3 ground states along this line. So up here, there's 3 ground states, which the plus, 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 minus, minus, this, and then this sum over all states, the sigma x. And to combat Eduardo's complaint that these are exponentially split, there's actually a point here. If you take at lambda equals 1, so not that much further up, just right up there, these are exact ground states. So Hamiltonian's the sum of projectors. And so what's remarkable now, this duality, oops, this got erased, is that the duality maps between these ground states. So in physics, when we have degenerate ground states, that there's no symmetry. So there's no spontaneous symmetry. Just ground state A is the same energy as ground state B, Well, that happens at first order transitions, because what happens in one phase, one ground state wins, you tune some parameters, in another phase, the other parameters win, and at some point in between when you tune the couplings, they cross and you get these degenerate ground states. But here, that's true, except one thing is much better here. We can locate this transition exactly, because the non-invertible symmetry, the D, between all three ground states. So this is why we can locate the transition. So even though these aren't the exact ground states when I move lambda off of this, it still maps between all three ground states. So again, you can't continuously change 3 to 2 or 1. The only option is for there to be 3 ground states until you hit another transition, which turns out for this case is infinity. Then something interesting happens. But when you have only this term, forget the Ising term. Anyway, so the duality is telling you something really important. It's locating exactly the first order transition line. You might say this is a little obvious, but there's some other ones where it's not so obvious. Okay, perfect timing.
I have a comment.
Okay. What?
If you have only that term,
Yeah.
that's an SPT.
It's actually a lot weird. No. The SPT, there's an important difference. It's not. The SPT is this. This is the SPT. So it's not the same. This is a model. If you have just this term, it's a model I named free fermions on disguise, and it's super cool. Ask me about it. But it's not related to, it's not an SPT. Oh, no, it's very, but good. So I went on, but. All right, good. Yeah. So again, in the sense of that over there, yeah, that's right. Yeah, so you have to be a little careful. So actually, the duality will actually annihilate the linear combination, the plus minus the minus, but then maps. Yeah. So because we got 3, so we can't. So what happens? It kills the all pluses minus all the minuses, and then maps between the x eigenvalue and the other one. Exactly. And like I say, those are exact ground states, finite size. There's no exponential splitting. At lambda equals 1. Elsewhere, there's exponential splitting. And but then it'll say, so it says something that there still is then a even on a finite lattice, it says there's a double degeneracy between the deformation of the one in the positive terms under spin flip. So and you wouldn't know that if not for the non-invertible symmetry. That statement remains true everywhere as long as you're in this phase. Yeah. I didn't show it, but roughly say, because we had this statement I said quickly, which was that DHJ equals H, K, I was calling it K hat D, which if you think about it is that this is like sigma Z, say, and this becomes a sigma X. All right, and so when you do this and do a translation invariance, you see that it maps that. Sorry. I needed to add the other one. Yeah, sorry, thank you. Sorry. These actually commute with each other, so I always forget them, but anyway. Yes, thank you. So yes. Yeah, if you're doing the classical, so Herman's question is this high temperature, low temperature. If I were doing the classical model, what Kramers and Wanier were originally doing, this would be called high-low temperature duality because it's ordered at low temperature or disordered at high.
It's also a mapping of sectors.
Yeah, absolutely. Same. no. So that's what I'm saying. So right. So it would map if we did it on a strip. It would map the model with free boundary conditions at both ends in our strip to that thing. And if I did periodic, then you have to do sectors. And if you did it on the torus, you then have to worry about sectors in both directions. Absolutely, yeah. Every single thing goes through. In fact, I spent a long time with my collaborators on this, convincing them that the classical model is actually the best way to understand this. So our paper is written in terms of the classical model, because honestly, it is the best way, and then you just take the limit if Hamiltonians are what floats your boat. So. Okay, I think we've had enough at lunchtime. Okay, good. Anyway, thank you.